Dear colleagues, dear friends, dear students, I'm very happy to present today some information, some results on our research on cold water coral reefs. Reefs generally, or coral reefs, are normally thought to live in warm water areas, beautiful landscape, blue sky, transparent waters. If you have a look to those environments, Tórshavn, Faroe Islands, Galway, Ireland, certainly sitting there in a pub you won't have an idea that offshore there are corals, and not only corals but real reefs. And especially when you're there on the ship with such a high energy environment, even it will tell you, is it really an area where we expect corals? Well, walking on the beach already you learn something different, because the beach is white and it's not black, and all that white stuff is derived from rubble and coral material which has been disintegrated due to wave action. But again, the Irish waters, where most of the spectacular cold water coral reefs thrive, really do not like a reefy area. This is what actually people have in mind when they think of coral reefs, you know, pleasant Seychelles or somewhere nice places in the Pacific region, but not cold, windy, stormy. But let's go back. Cold water coral reefs or cold water corals have been known for many, many years, even for decades. But that it was really a reef-forming coral that was in a way rediscovered by my good friend Michael Ivanov, who unfortunately passed away 2 years ago. He was the leading scientist of this famous and very successful UNESCO program called TTR, Training Through Research. And with the Logachev, they were traveled in the last decade of the last century to the Porcupine Sea Bight, and they studied there especially those areas surrounding the Porcupine Sea Bight, the flanks and the chondrite areas there. Unfortunately, I had not a good shot from the Logachev, and so I just took our own ship, the Poseidon, and they were running several hydroacoustic lines over that area. Also some seismic lines, not only swath bathymetry, they also shoot some seismic lines. And when doing this, they discovered beautiful sections of transparent material. What is that? Is this maybe a shallow gas or other things? And then it turned out it must be carbonates, huge carbonate bodies. And then by applying ground truthing, it was all full of living cold water coral. So although we had many ideas from previous publications that cold water corals occur in these regions, no one at that time really had an idea that they couldn't form mounds as high as it is here being portrayed in this seismic line. From the geological past, we know these structures. Many of them, through the Earth's history, are widely distributed. These are maybe the most spectacular ones, the Devonian Tidili Mountains of Upper Devonian age. And already, since these structures have been known to host, at least in some areas on our globe, major oil and gas reserves, this was already an area being addressed from James Lee Wilson in 1975 as the so-called DDD environment where they live. And these three Ds stay for dark, deep, and dirty. And dirty means a lot of nutrients. Okay, so at that time, we had really no idea, and many reef carbonates always assigned those bodies to the shallow water. And there was a long debate until the beautiful discovery of these modern cold water mounds in the Irish waters. And then suddenly, many of these ancient cold water or ancient carbonate bodies became cold water coral reefs and deep water coral reefs. Now, in contrast to the modern cold water corals, in contrast to the modern shallow water coral reefs, there are only a minor amount of real scleractinians taking part in the formation of these cold water coral reefs. We have about 673 species which are zooxanthellates. So they have no zooxanthellae living with them in the symbionts in their tissue. It's about half of it. 175 species out of these zooxanthellate corals are colonial. But only 10 species, which is less than 1%, are frame builders, creating a real frame building. And here are the major players in this game. This is Lophelia pertusa, this is Madrepora oculata, and another morphotype also from Madrepora. I mentioned already that cold water coral as a species, as a skeleton, has been known for long, long times. Known since the Middle Age due to fish catches of Norway. They were always in the nets. Lophelia pertusa has already been described by the Bishop Gunnerus von Bergen in 1758. A very good description. Since that time, we know it forms a carbonate, a solid carbonate skeleton. At that time already people were, guessing, assuming that this coral has a growth rate of 1 to 2 centimeters per year, although not proven by any proof. Of course, it is carnivore, and the temperature window in which Lophelia pertusa, the most prominent cold water coral frame builder, lives is between 4 degrees centigrade and 13 centigrades. This is a photo of a sample. You see here the scale, 2 centimeters, so one callus is almost 2 centimeters length. Let me just briefly touch on what we knew before the famous Michael Ivanov expedition rediscovered them in the last century. Already in 1872 there have been some first echo soundings and some dredges, but at least that one, look at this, is an ancient echogram of a cold water coral reef. No one at these times had ever an idea what that means. It was just a bumpy surface, whatever it is. But now we know from where this line is, so certainly these are cold water corals. So large reef-like structures, concentration along the continental margins have been at least portrayed. And it was Le Danois, a paper published in 1948, calmly rested in the drawers or hidden in the second but last shelf in the library, overseen for decades, has published this nice map of Europe, where all the living cold water corals, according to his vision, should occur. These occurrences now have been proven that they exist in reality. So these cold water coral reefs obviously form large reef-like structures. They have a concentration along the continental margin. They have a high biomass and a diversity, and unfortunately for them, are the main areas for fishing. Now, maybe even argue that these cold water coral reefs of Europe are the largest barrier reef of the world, larger than the Great Barrier Reef of Australia, it looks like. This map shows the dots where we know cold water coral reefs occur, and actually every year we can add more than 20 new dots on that map. So it's in growing information. On the other hand, of course, these cold water coral reefs thrive in a water depth which is not very pleasant for divers, far out of the reach, so we need other means to study them. Either we go down with small submersibles. This is Geomar submersible Yago being used here with our Poseidon, or we need some remote operated vehicles like the new one Foca we have just recently purchased at Geomar, or with the big ROV Victor. Now let's go on a small trip to those reefs of Norway first. This is the Stjernsund area, one of the northernmost sites with Lophelia framework, but I have to correct it now. Last year in fall there was a nice publication showing huge Lophelia build-ups off the northern margin of Svalbard. So these are now the northernmost living coral reefs on the world. And the other area is the Rest Reef, also on Norway, where we have deployed our submersible Iago. As I mentioned, we have to go down with either prolonged ice in terms of a remotely operated vehicle like this FOCA, or with the submersible. Now let's dive down, and we go deeper and deeper, and it's getting dark. Deeper than 500 meters, absolutely pitch dark. Lights on, please. And suddenly we see these nice reefs. Spectacular. Spectacular as shallow water coral reefs. Of course, not as highly diverse with respect to skeletal material, but as highly diverse with non-calcified organisms. A lot of Lophelia, Madrepora, large crabs, fishes, beautiful colors, impossible to see with a naked eye, with a normal eye. So I don't know why these colors are there. Our colleagues now from Aberdeen, they have developed a special camera system to detect how fishes catch their prey in the deep. And obviously there is much more bioluminescence in the deep water than we have previously thought. And with that bioluminescence, of course, all these colors are visible. Some pictures. This is the Rest Reef, an old moraine covered with sponges. These are some soft sponges, no corals here so far. But another nice species, not calcified, the so-called bubblegum coral, Paragorgia. Bubblegum coral because you know when you know these strange Americans always chewing on their bubblegum, making these bubbles out of the mouth. Not very pleasant. And then when the substratum gets more and more rigid and hard, then suddenly Lophelia shows up. This is the Lophelia thicket. You see here some nice crabs in between. A small crab called Munida lives with, very jointly with Lophelia. This is my favorite view of Lophelia Reef. This is within the Stjernsund. We were diving with our submersible, and Jürgen, the captain of the submersible, said, hey, come on, please switch off the microphone. If they listen to what we are saying, they believe we are doing something completely different and not looking to the coast, because you know we were so overwhelmed. We were driving there for, let's say, half an hour, and the thicket doesn't stop. So beautiful. This is a view from the continental margin of Ireland. In this hydroacoustic surface image, you see all these small bumps coming up there, all mounds covered with living cold water corals. And this is just ground truthing that we are really dealing with these structures. There was a very interesting swath bathymetry campaign in that area being performed by our colleagues from the Alfred Wegener Institute, which they produced a nice animation. So it's actually like you are flying over these structures, and this will be shown in this, hopefully it is running. Yeah. You see, we are just here in the west, looking to the east. Somewhere here is Ireland. This is the southern tip of Ireland. Somewhere here we are offshore. This is the so-called Gallen Channel. We are now going still in a east direction, now turning up to the north. And we see the Irish Shelf being dissected and intersected by several of these canyons and gully systems. And there up in the north, you suddenly will see how small mounds pop up from the surface. And this is the most spectacular reef site of our European continental margin. We are almost now flying in that area. And all these build-ups, these are these huge, really huge carbonate mounds living there on that margin. Okay. Let's have a closer look to these mounds, Therese Mounds and the Moira Mounds, very closely together. The Moira Mounds is what we may call a juvenile reef, which just starts, or let's say is just in the stage of developing a real structure. It is highly protected, although none of these reefs are so far a marine protected area. These Moira mounds, attract or have a very special shelter. These pictures were shown from our British colleagues to their government, and they convinced the British Navy to run here permanent maneuvers over the reef area, so fishermen are off. So the Navy protects nature. Very interesting approach. Okay, let's have a first look to the Moira mounds. A small juvenile startup. These are the Moira mounds seen in the side scan sonar. You here see the scale, just 50 meters, so very small. They are surrounded by a ripple field, sand ripples. Some small coral colonies start to grow there on some sporadic hard grounds. So any shell, any broken coral piece could be a sporadic hard ground, which is enough for a coral to settle. But in some areas, the Moira mounds already started to grow together and form a small miniature framework. This is also a very nice picture already on the lower right of a larger block of Lophelia. The Therese mounds look a bit different, also surrounded by a large giant ripple field caused by these contorite flows. But you see already the major difference to the Moira mounds. Between these living Lophelia, you see hard rock. And this is really damn cemented. You have no chance to get any sample out of it. You need explosive to crack the rock. It's really well cemented. A close-up, and it was nice to see, these coral branches, according to our experience and impression, show normally up to 15 living polyps on top of each other, no more. So if then the next one is being formed, the lower one starts to die off. Here it is nicely seen in this close-up that there are several polyps growing on top of each other, and according to our present-day understanding, such a single polyp is being precipitated or formed during 1 year. And this is a close-up shot. Now, what is the size? Do you have an idea of the size? One of my former PhD students, Andres Rüggeberg, with whom I have published quite a lot of papers together, worked on propeller mount in the offshore Irish seawaters. And while working there, he was quite familiar with this map we created. And while working up to his office room, he always passed by a map where Helgoland was displayed. And suddenly he realized, these are the same dimensions as the island of Helgoland. Let's make a simple comparison. So here we see the shape of Helgoland, and here we see the shape of these mounds. So we are not talking about some sand grains below our fingertips. These are really masses of carbonate being precipitated there. Okay, now some small impressions of life in the reef. Corals, sure enough, this is Lophelia pertusa. Desmophyllum christagalli, more a species being more common in the Mediterranean. These two are not calcified species. Both could be addressed as the bubblegum coral. Antipartarians occur. Proteanthea, also a non-calcified species. And these are two sponges. And then here a nice shell Archester, which is presently being explored as an archive for better understanding paleo-environmental changes, since Archester has quite a long life, and you have nice growth spans, and these growth spans can be analyzed by applying certain proxies in order to better understand how the reef has developed. This is just to show you the beautiful aspects of these environments. Nice octocorals. Crinoids. Some of these mounds with dead corals are covered with living crinoids. Suddenly you have the feeling, well, I'm looking back into the Upper Carboniferous. We know a lot of these mounds covered all with crinoids. Huge amounts in Earth history, nothing than the rubble of crinoids. So this could be maybe a kind of impression of it. Life in the reef, fish, sure enough, there are many. This is one of the most endangered species, the so-called orange ruffy, because this is, how to say, a hot topic to have it on the menu, and better you don't eat it anymore. Now some aspects on the oceanography. Is there a control? Why are these carbonate mounds there where they are? Already 2002, André Freiwald pointed out maybe the density contrast, maybe water masses may play a certain impact on that. This is a water mass sketch offshore the Galicia Bank, so we're Spain. We have the North Atlantic deep water, we have the Mediterranean outflow water, and we have the North Atlantic central water. And here you see nicely a contrast, mainly due to a contrast in salinity. If you move up to the north, to the Celtic margin, we do see similar situation. We have again the same water masses, North Atlantic deep water, and also the Mediterranean outflow, and again here this contrast. And even if you go up to the Norwegian margin, of course, high up in the Norwegian there are no more real traces of Mediterranean outflow water, but again we have contrast either between the North Atlantic deep water or the North Atlantic central water, and mainly in those fjord settings with the moat water which is being produced in the winter and the North Atlantic central water. All the living coral reefs obviously have something in common with this density contrast, and we did a lot of oceanographic measurements. First, I was so convinced that there's something behind it, and I went to my colleagues from the Department of Oceanography and showed them the first maps and said, forget it. I mean, this was just a hit and go measurement. You need 10 times of measurements. So I was really appointed being a geologist, asking my colleagues, more or less being kicked out of their office, saying I'm ignorant. Well, what we did, we started to measure several years, and now we have a good data set. This shows you how high energy this environment. This is our colleague, just he wanted to sieve some material and he was not paying attention, suddenly got a nice shower over the side. And this same high amount energy is also in the area where the corals are living. This is a lander equipped with an up-looking and a down-looking ADCP to measure the currents, also to measure the sediment which is being accumulated during the year. These landers are deployed with some weight on their feet, and when their mission is over, you just release the weight stays on the seafloor, and the lander is coming back up to the surface, and you have a good data set. Well, this just shows you how such a lander is being deployed on the seafloor. This is the camera on top. Now the lander was just deposited, and then you hook off your deploy system, and you see your lander resting peacefully there on the seafloor within the corals, and there it starts its measurement. We recovered this lander after 4 months, but the record was not as good as we wanted since we had an instrument failure. These camera systems especially failed. They should be waterproof, and in a way they were waterproof because we were shaking them when we had them back on the surface, and the water which was inside was not coming out, so they were exactly waterproof. But what it shows you nicely, this is the up-looking and this is the down-looking current data, and you see the classical tidal cycles. So even down there in 600-meter water depth, a full tidal cycle as it is necessary also for the shallow water reefs. So the physical parameters seem to be quite similar. Seasonality. With the sediment trap we collected a lot of material, and you will see that the so-called spring bloom, which occurs in these waters around April, May, start to settle down there in the reef around maybe September, October. Unfortunately, we have not a full year cycle. But anyway, we then studied some isotopes, and you have to be very carefully where you study your isotopes. This is so-called an uncontrolled measurement. Here we did a very controlled measurement, only analyzing the septa and not the wall, and then you see a nice peak, a zigzag pattern in the carbon isotopes, and that is in relation to the nutrition. So the nutrition peak which comes down there September, October, gives the kick to the polyp, it starts digestion, and then it's more a phase of silent. A bit more to the oceanography, the water masses, especially in that area up there. We have the surface water, but also we have the contourite waters, which belong to the intermediate water masses. And here again, it is nicely seen, you know, we have the surface currents, we have the East and North Atlantic water, and we have the Mediterranean outflow water. And exactly where the highest salinities can be seen in the water column, this is the water depth where our living corals, our living cold water corals do occur. We have measured a so-called section over this area in the eastern porcupine seabed. You see here several of these mounds, the Galway Mound, Therese Mound, the Poseidon Mound. And when you plot, according to this section line, the water mass characteristics, the upper one shows the temperature, the second one shows the salinity, and the lower one shows the oxygen. You nicely see that this is the upper surface water, or let's say this is the surface of the Mediterranean outflow water, where we have this density contrast. And here you see Poseidon Mound is above the surface, and Poseidon Mound is damn dead. No live corals. But that one, the Therese one, is beautifully thriving. So again, this water mass density contrast has obviously to say something. We then, from these areas, from Ireland up to Norway, investigated the relationship between the salinity and the temperature. This is so-called TS plot. And there it shows that most of these corals are just above the intermediate salinity maximum, which is, with respect to density, 27.5. In other words, 1 cubic meter of seawater weighs 1,027.5 kilograms. These are the plots for the Irish sites, and if we just move up to the north and have a look to our Norwegian sites, we see exactly the same. So there is a very close relationship for this temperature salinity in order to find these areas. What about other sites going further to the south? Captain Arutinov mud volcano within the Gulf of Cadiz, also known for its corals, but as you can see here from these pictures, they are almost all dead. No living Glophilia, except some rare Caryophylla, which is a non-frame building cold water coral. We investigated there the water masses in the same way, and where we do have the dead coral assemblages, we are below. So we are not within this depth window. Same with Morocco. Morocco is above. So crazy corals. Why do they stick to this density? Does a coral feel density? I don't believe. But if this is a contrast, a density contrast, then the nutrition. Please remember what Wilson already in 1975 published. DDD, dark, deep, and dirty. We need to explain the dirty. That means nutrients. So if there is a density contrast, nutrients may concentrate on this density level. And then the other corals are, colleagues, enough to foot, come on, that's a good site, let's stay there. One idea. And the other is, which is not proven, this is still a hypothesis, since we will never ever been able to see and collect larvae from these corals. But the assumption is that the larvae, the unmetamorphosed early stages of larvae, have a density a bit less than this density contrast, and just like a surfer on the waves, they are floating around, and when they hit a hard substratum, they start their metamorphosis. So if we are very keen in getting a larvae in order to prove or disprove this hypothesis. We have also looked at another boundary condition. a part of this sigma theta value for these modern Atlantic corals. By the way, we proved it that this is also valid for the transatlantic species, the so-called west side story in the Gulf of Mexico, same density level. So it seems to be a kind of predictive tool if you would like to find living cold water coral reefs or living Lophelia reefs. Now, a part of this special density contrast, what about dissolved inorganic carbon? And what about total alkalinity, with other terms, pH? Does this also influence the distribution of our cold water coral reefs? This is just a paper which came out this January by Sascha Flögel, myself, and some colleagues. Since we have many, many data points and many water samples, we started to measure the DIC content. This is again our density envelope we have published already earlier, and here we see the DIC. These green, blue, and light blue dots represent those coral reefs or those cold water coral reef occurrences which have a real pristine reef growth. Those which are here in white or in yellow, and of course this extreme group up there, they are from sites where the coral growth is not as pristine, except the Mediterranean, which has a high amount of alkalinity due to the high river input in the Mediterranean basin. Now obviously DIC seems to be a limiting factor if it's above a certain concentration. That means if it's higher than 2,170 micromole per kilogram, then obviously corals suffer. Why? This graph shows you the relation of DIC and total alkalinity. If primary productivity is being enhanced, then the DIC would move in this way. If respiration is being increased, we move in this way. If CO2 is being released from the ocean into the atmosphere, it's going this way. If CO2 is being uptaken by the ocean, we are moving in this way. CO2. It is a limiting factor. We produce a lot of CO2. So obviously, if the CO2 concentration impacting on the DIC, then our cold water corals have a problem. And also with respect to pH, which is unfortunately not so clearly seen. These are these lines running like here. That's why the Mediterranean have almost the same pH than our Norwegian sites there. So DIC is another important factor. Now, another short story. Can we measure paleodensities? You know, being a geologist, we always would like to go back with our proxies in the time. There was a nice ODP, ocean drilling activity on these so-called mission platforms. They drilled in these most beautiful cold water coral reefs of Ireland. This is the right sketch shows you the setting where the sites are. And we compared the drill course with a course we took before several years ago and see if we could in a way get an impression about paleodensities. Here we see a core taken from the propeller mount, and these dates indicated here show you where we have absolute ages taken from the corals. And all dates so far we got show that corals only form obviously during warm stages. There's no real documentation that during extreme cold, that during extreme glacials, that these corals are living there. There is one information we can get out of this graph. The second site we analyzed was this beautiful ODP site, site 1317 with several holes. Here you see the hydroacoustic map. Here you see the sketch through Therese Mount. Challenger Mount, sorry, not Therese Mount, Challenger Mount. This is the core, the general core, how it looks like, to make this complicated story a bit easier to understand. This is the base of the mount. The initiation obviously occurred 2.7, 2.5 million before present. The mount evolution has its highest peak during 2.6 and 1.6 million years before. And then there is a large hiatus between 1.6 and 0.9. And since then, the mount, in a way, a bit is declining. Now, how did we this approach? Paleodensity estimation. There was a very interesting paper by Stieglitz and co-authors in 1999, in which they tried to correlate the oxygen isotopes from benthic foraminifera also with respect to salinity. The normal relations is that the oxygen isotope of the benthic foraminifera minus the oxygen content of the water, that gives you the temperature. And this is shown in the right graph. And there's a strong linear correlation, which we all apply for paleotemperature, sure enough. But there's also a correlation between the delta 18O of the seawater and the salinity, which is being displaced in the lower graph. It's just the other way around, but there is a strong correlation. Now, could we correlate this, the carbon isotope with an assumption of the surrounding seawater from benthic foraminifera we collect in the course to the density? In a way, here it is shown that the delta 18O of seawater, how it correlates with the density, with the salinity. This is what I have shown already earlier, the relation between temperature and salinity and the density. So we have two, we have a salinity estimate and we have a temperature estimate, and by this we can calculate some densities. There is a so-called fresh end member. This is a complicated equations. These are only for the specialists. There's the global ocean equation, which has been published by Stieglitz et al. In 1999. And out of this equation, we deviated a Florida Strait North Atlantic equation. And this is what we applied for our North Atlantic Tzibizidis stuff for the Challenger mount and the propeller mount. This is first our propeller mount. I just would like to recall our absolute ages from our corals, and then based on our salinity and temperature estimates derived from these benthic foraminifera, you see that most part of the prolific coral growth is within this depth range of 27.5. And the same we applied for the Challenger mount. We checked the benthic foraminifera below the mount base where there was no reef. And you see we have a paleo density of 26. And then as soon as the mount starts to grow, we are within this 27.5. So obviously there is what we have seen, which is applicable for the recent, also can account for the fossil record. Now, at the end, I would also briefly touch on a very critical issue for these cold water coral reefs. They are really in danger. They are in danger, first, acidification. I mentioned the DIC problem, but I would say the greater problem is fisheries. Since these beautiful cold water coral reefs are what you may call the cradle of our living fish, or the nursery rooms for our fish, because they have a lot of space to hide, if we destroy them, then fish have problems. 4 to 6 tons per day are being taken out of the oceans, an area of more than 10 square kilometers per day, or let me put it in other words, 4 times the size of the United States of America are being bottom trawled every year. That is a problem. Cod, red perch, to name a few. Deep water trawling is now going down to 2,000 meters and even deeper. So fishing, I would say, is a serious concern, and I would say the cold water coral reefs may suffer in the near future more from fishing than from global change, although this also may impact. You see here some shots taken with the RAF Victor through Ifremer, where there are some fishing nets remains seen in one of these cold water coral reefs of Ireland. You see here a small crab which has no chance to get out of this rope, how to say, salad. Or here, large blocks of cold water corals entrapped in these fishing lines. The orange ruffy I mentioned, extremely chased fish. How long does it may exist? We don't know. This small animation shows you how critical bottom trawling impacts on cold water coral reefs. This is just a shot how beautiful these reefs are. This is an area when bottom trawling was running over the field. And these are huge. This is also a nice shot. Where should this poor fellow hide himself when there is no more to hide? And this is a very nice, not only animation. In the next few seconds you will see they have a movie camera mounted on one of these bottom trawling nets. And this is, yeah, you see here, there's a camera mounted on the nets. These huge rollovers just run over the blocks, and it's almost like a tank was running through a forest. Nothing rests there anymore on the seafloor. And you see huge impacts leaving behind. Also here, bottom trawling, you see the marks. This was a living reef, completely destroyed. If you think of a polyp that size needs 1 year, hard that they will ever recover. We found large areas where corals have been just thrown over the side, huge accumulations of trash, all dead, all like the lower one here. So cold water coral reefs are unexpected, beautiful ecosystems on our globe, everywhere where the cold water is, but as I mentioned, really in danger. And with these few beautiful, nice shots from this beautiful, highly biodiverse life down there, I would like to conclude and also would like to thank you for your patience and for your attention. Thanks a lot.
Thank you very much. Excellent presentation, and I hope we will have some questions. Please ask the questions. And could I ask the first question about MPI? You mentioned that there are some marine protected areas, MPA.
MPA, yeah.
Yes, and only few of these areas are covered by the...
So far, none of these European cold water coral reef sites are under an MPA. We are still working on it. And except the small one I mentioned, which is under the shelter of the British Navy.
But is it inside of economic zone? Easier.
Yeah.
And so this is Ireland, this is Great Britain?
Ireland, Great Britain, Norway, France, sure enough, Portugal, Spain, Denmark. So in Norway, Norwegian laws are more rigid. When you have a Lophelia in your hand and the picture is shown in the newspaper that having a Lophelia piece in my hand, no way to escape, they will arrest me. So it's not allowed to take off any Lophelia except you have a permission. and they have decided where you only can take now samples. But the other countries have nothing issued so far. Big problem.
And another question is about power aspects.
Yeah.
So these two types of reefs, as I understood, in the present day environment, they exist both types. And what about the paleo records? If you can find both of these types in paleo records as well? Yeah.
Yes, there are. Especially the Devonian. The Devonian nicely shows these two different types. So the majority of the Canadian oil is located within these cold water mounts. So the subsurface of Alberta, this is a classical cold water coral reef province. If you go, for example, to Western Europe, Germany, Belgium areas, the lower Devonian cold water, the upper Devonian shallow water. Also upper Devonian Canning Basin reefs in Western Australia, shallow water. So we have the two types through all Earth history.
And what is the main criteria to compare to this picture?
Right. I would say the classical geometry of a cold water reef is a mound-like structure, right? And the facies patterns are, in a way, symmetrically arranged. You will not differentiate in a cold water coral reef between shallow, forereef, and back reef. You will only differentiate between the reef and the talus, and the talus is all around. While in a unidirectional wave exposed reef, you have the shallow and calm area in the lagoon, and you have the high energy and with the large blocks in front. So if you clear a zonation. So if you have a unidirectional facies pattern, then you're in a shallow water reef. Okay?
And mineralogically, they're the same.
I would say to fulfill the requirements of James Lee Wilson, the cold water coral reefs need more mud, dark, deep, and dirty, right? They have more mud. Okay, but porosity evolution, it's the same.
Yes, please. More questions.
What is the age of the oldest Ophelia pertusa?
Good question. A lower tertiary, but I can't tell you exactly the age. There are fantastic outcrops in Denmark, near the shore, huge Ophelia reefs. They are of Miocene age, and there are some Eocene known Ophelia to occur on Rhodos. But older, I don't know.
You showed the northern part of the ocean. Do you know something about the southern oceans?
Sure. There is, maybe I quickly could pick up that slide before I showed that map. Here are some spots seen also in the Southern Ocean. We have now information, especially around offshore Brazil, that there are nice mounds. So far it was difficult to get information because this is all under the concession of Petrobras, and they keep their information in their desk, you know. But now they are willing to open it. And here, there are many, many more dots now. This is the Chatham Rise. There are many Ophelia. But during our Kalmar project, you know, we were trying to find some up here. Bubblegum corals, yes, a lot. Easy deed corals, yes, a lot, but no Ophelia.
In the Chatham Plateau, if they associated with phosphorites or not? Or phosphorite is deeper?
It's deeper. Oh, sorry. Yeah, that's much deeper. That's deeper. That's deeper.
Are they similar as in North Atlantica?
Yeah.
Or same species?
People working on genomics start to fight. But I would say with respect to species, yes. This is it's maybe below the species level.
You also showed a picture with coral corals to the south of Australia.
Yeah.
Same.
There are also some here, down here. Yeah. There are some. Okay.
Okay. More? Yes, please.
I'm wondering if someone did or does mapping of cold water reef distribution, something, some schemes.
This is a scheme.
This one.
What do you mean?
This is very general, but I mean, if someone uses space images and trying to monitor the distribution.
Yeah, it is difficult since they are so deep to monitor them with some devices. What is normally done? We have one colleague now in Germany, affiliated with the Senckenberg Museum, and he is trying to gather all the information on a map. And this map is always growing. This is the only way how we really could get this ongoing information. Monitoring of a living site, yes, there are two sites. One is in the Oslo Fjord, where there is a so-called video control, an online control on this one. And this is an area where we are very keen getting in, because these video cameras took pictures when the corals were spawning, so we could get the larvae maybe. And the other idea is also to do a continuous monitoring in the Irish waters, but this is still not being set up. Okay? I hope this was the answer you were expecting.
Well, and could probably something be done to protect the reefs, and what should it be? Just by people? Are there any, I don't know, ecological organizations who are already doing something?
There are plans to at least to create some marine protected areas, sure enough. The Irish Sea, especially the Porcupine Sea, is also interesting from another point of view. The Irish Porcupine Sea hosts also some oil and gas in the deeper subsurface. Maybe you disagree with me, but I tell you, the best protection for these reefs would to set up there a rig. No fisherman wants to lose his nets in the rig. So what was completely done wrong at the end of the last century, when the Brent Spar disaster we were facing, which I don't know, maybe you remember, there was this platform in the North Sea, northern North Sea, the Brent Spar, also, by the way, surrounded by some living corals. And all environmentalists we have to get rid of, they are ruining the ocean with their crude oil, you know, and then they took it out, and now the reef is dead. If this rig would have remained there, that would be a nice spot for the corals and fish to survive.
And last Navy, as a protected.
Sorry, what?
Was Navy as a...
The Navy. Oh, you asked the Navy to do it. Yeah. Okay.
Okay, so thank you very much once again.
Thanks.